Good morning, I'm Alejandro Martinez from the Joint PhD program between Politecnico di Torino and INFN Torino. Currently, I'm collaborating with DarkSide Framework for searching that matter particle. In this project, I'm working in the design of the front-end integrated electronic for the readout of large area sensors such as silicon photomultiplier at 87 Kelvin. The electronic is focused on underground Astroparticle physics experiment that is used to detect the neutrino and dark matter particle. In this case, the DarkSide 20K experiment is described by this structure. Basically, this chamber is filled with liquid argon that is used as a scintillator, as I described this figure. The scintillator enters in contact with the incoming particle and generates scintillations. The generated photoelectrons are detected by the silicon photomultiplier located in the top of the chamber. The silicon photomultiplier are composed by several tiles of 24 cm² with a total detector capacitor of 10 nanofarad. In order to realize an optimal IC design, a characterization of this structure at 77 Kelvin was mandatory in order to extract the most important parameter of a transistor, like a transconductance, low field mobility, and threshold voltage. These tests were realized in the partnership with the foundry. Well, the setup that was carried out in order to test the green electronic is described in this figure. Here, the board that contained the integrated circuit plus the sensor are together inserted in the viewer full of liquid nitrogen. Additionally, the optical fiber is inserted in order to provide the photoelectrons inside the viewer. As a result, we obtain this peak voltage histogram. Basically, this histogram is conformed by the amplitude of 10,000 output signal waveform, and basically each distribution conforms its photoelectron. For instance, this is the single photoelectron distribution, 2 and 3 photoelectron, and so on. The figure of merit of this experiment is the signal-to-noise ratio. So in this case, it was computed in 9.6, much higher than the minimum requirement of the experiment that was set at 8. So the result were described by the collaboration as excellent, and for this reason, this prototype was chosen as a baseline of the integrated electronic within DarkSide 20K experiment. In other words, this Cryogenic electronic will be included in the final prototype of the DarkSide 20K experiment that will be running in a couple of years. Additionally, in order to improve this figure of merit, we implemented a real-time digital filter on FPGA at 125 MHz. The results are described in these two figures. This is the pre-filtering histogram, and after the application of the DSP, the figures of merit, the signal-to-noise ratio was improved around 50%. Furthermore, in order to improve the reliability of the experiments, we proposed to the collaboration a new prototype with a differential output signals instead of single-ended signal, because the differential signaling allowed to the output signal to be driven from the Cryogenic environment to the word data acquisition system by cabling instead of optical fiber, because the optical fiber could suffer some damage due to the low temperature and reduce the reliability of the experiments. Here was the simulation and the layout structure that was submitted last year. We already have the chip, but we couldn't test it yet due to the current situation. But probably we will have some results in the next month. Well, in conclusion, the next generation of that matter and neutrino experiment will implement large area silicon photomultiplier as a detector. So this prototype will be really useful for this future experiment because it provides a good efficiency, and it was realized with a cheap CMOS technology. Thank you for your attention.